Welcome everyone. In this video we'll look at electrochemistry and electrode potential from year 2. The first part of the question is on oxidation states. Great revision for both year 1 and year 2 students. Let's get started. Here's the first part of the question. Deduce the oxidation state of nitrogen in NO3- and in NO. There are rules and guides for assigning oxidation states. It's a good idea to memorize them. For ionic substances, the oxidation state of each simple ion is equal to the charge on the ion. Combined group 1 and group 2 metals have an oxidation state of +1 and +2 respectively. Combined hydrogen has an oxidation state of +1 apart from in hydrides, -1. Combined oxygen has an oxidation state of -2 apart from in peroxides where it's -1. The oxidation state of atoms in an element is 0, and the sum of the oxidation states is equal to the overall charge on the compound or ion. Using these rules and guides, the oxidation state of oxygen is -2 in both species. I have put the total negative charge from the oxygen below each species here, -6 in the nitrate ion and -2 in NO. The NO3- ion has an overall charge of -1, so the oxidation state of nitrogen must be +5. The overall charge of the NO molecule is 0. It is neutral. The oxidation state of nitrogen must be +2. The oxidation states of nitrogen in both species are given in blue. Next, we are given a table showing the standard electrode potentials of a selection of half equations. Standard electrode potentials are measured under standard conditions, 298 Kelvin, 1 atmosphere, and solutions must be 1 mole per decimeter cubed. These are the values of potential differences in volts that will be measured if each cell were connected to the standard hydrogen electrode under standard conditions. The greater the value of standard electrode potential, the more likely that equation is to proceed in the forward direction. Here's the next part of the question. State the weakest reducing agents in the table. Reducing agents are oxidized. They lose electrons. In each of these half equations, the oxidizing agents appeared on the left and the reducing agents appeared on the right. The standard electrode potential of the chlorine-chloride half equation has the greatest value. This is the least likely to proceed in the reverse direction, so chloride ions are the weakest reducing agents here. Here's the next part of the question. Write the conventional representation of the cell that has an EMF of plus 0.43 volts. To work out cell EMF, electromotive force, use the equation E cell is equal to E most positive minus E most negative. Identify the half equations that give this EMF. For conventional cell representations, a single line represents a phase boundary. Think about solids, liquids, gases, and aqueous solutions. Double check the state symbols that you are given. A double line represents the salt bridge. The oxidation electrode goes on the left, the reduction on the right. Commas separate different species in the same electrode in the same phase. Here, the answer is given in blue. The platinum electrode must be used for half cells where no other solid appears. It's very unreactive and provides a surface for the electron transfer to take place. Here's the final part of the question. Use data from the table to identify an acid that will oxidize copper. Explain your choice of acid. Use these data to suggest a possible equation for the reaction. Calculate the EMF of the cell that has the same overall reaction. Remember, an acid is a proton donor. There were 2 half equations in the table that were linked to acids. I've deleted the other rows apart from these and copper. Let's address the first part of the question. When two half equations are combined, the system with the most positive E standard value is reduced. Nitric acid is the appropriate acid to choose here. E standard of NO3 minus NO is more positive than E standard of Cu2 plus Cu. Next, we need to give the overall equation. Start by writing out the relevant half equations. When combining half equations, we need to make sure that they are balanced for electron transfer. The number of electrons lost in the oxidation half equation must equal the number of electrons gained in the reduction half equation. We have to multiply the top equation by 2 and the bottom equation by 3 before combining the two half equations. Next, combine the two half equations. Put all of the reactants on the left and all of the products on the right. Cancel any species that appear on both sides. Although this is not the case here, it is sometimes possible to cancel H+ ions and water molecules as well as electrons. It is good practice to give the lowest whole number ratio of reactants and products. However, multiples are often allowed in mark schemes. Finally, we need to calculate the EMF of this cell. E cell is equal to E most positive minus E of most negative. In this case, 0.96 subtract 0.34. This gives a value of plus 0.62 volts. Thanks for watching this video. I hope you found it useful. I welcome any of your comments, questions and suggestions. Please subscribe and click the bell for notifications. Take care and goodbye.